So hello, everyone. The good news at the beginning, it's the last presentation for today. So you're nearly finished. And I want to talk about the evaluation of dynamic fracture toughness. And maybe you will hear something again because the projects are related, not directly, but indirectly. You will see it. Maybe I want to introduce. Okay, maybe I would like to introduce the component which we are talking about. We are talking about the a cask for transport and storage of spent nuclear fuel, and the cask, the Castor, is a worldwide trademark of my company, the GNS. And one of the main components is the cask body, and this is made of ductile cast iron. And to give you an impression about the dimension, we are talking about a component which is 5.5 meters high, 2.5 meter diameter, and has a wall thickness of nearly half a meter. The casting weight is up to 160 tons, so it's really huge. And the cask has many safety functions related to ensure the safe handling of the spent nuclear fuel. It's a shielding function, it's the enclosure of the spent nuclear fuel, and the heat removal, and also ensure the subcriticality, which is the main function, especially. During the license process, we have many regulations. For example, the EIA regulation, which is relevant for the transport and storage for spent nuclear fuel. We have some national guidelines like the BAM GGR 7 and the regulation from Switzerland, the NCG 05. Then additionally some international standards like the FKM. And during the design process, we have to fulfill different requirements for especially mechanical evaluation, drop tests, 9 meter, and we have fulfilled or have to show some material and component tests. And this regulation has some special requirements. For example, the temperature, it's minus 40 degrees, and we have to exclude the fracture initiation. And the minus 40 degrees have some special things. And the thing was we have to determine the fracture toughness values of the casks, and especially during the license process. And so we developed it was necessary to develop a special test procedure because the handling of ductile cast iron, it's not standardized. We have shown, it was shown that we need much more samples to evaluate the fracture toughness. It has a high complexity during the preparation process, and we have a different material behavior than steel. And we did that not alone. We did it together with the Technical University in Freiberg, and especially the colleagues from BAM, the Federal Institute of Germany for Material Testing. They published also different results of this. You can find it, some examples at the bottom. And it was necessary to find a test procedure which is able to describe the material behavior for ductile cast iron. And we found out by a comparison between the two laboratories that we need much more samples for the fracture toughness evaluation. And we make some tests. How many samples are necessary to test until one data point has no significant influence on the final result. And the result was we need up to 15 samples. And 15 samples is really much. And so it was necessary to find a technique with a lower number of samples, that means a lower preparation effort and also a lower time to evaluate each sample. And we had a really good basis because we had the multiple samples technique with SEB 25 samples at -40 degrees. And the aim was to find a new test procedure or a test method to evaluate and validate this method by the comparison with the multiple specimen technique. And that was the thing. We tested these crack propagation sensors. It consists of 20 electroconductive lines with a constant distance, and each line leads to a voltage change if it's ruptured. And when we determine this fracture toughness value, it's important to find out at which time the fracture initiation takes place. So, and for this, we make a procedure to correlate this this crack line with the fatigue crack, and with this thing we can find out at which time the fracture initiation took place. After that, we can we can evaluate the fracture toughness of this specimen. At the end, we have to explain that it's only valid, this method, at the not really ductile area of the behavior, because we have to exclude massive plastic deformation at the surface of the sample. And that is the point. At static behavior or at static loading, we have different material behavior at ductile cast iron, and at dynamic fracture, dynamic loading at low temperatures, we have a cleavage fracture, and that is, in our case, not so bad, because due to this behavior, we can use this method. At the final step is to convert the evaluated fracture toughness into KJE values. That is necessary because most of the construction codes use these values. For the validation process, we had 5 different casted materials. It was some model material like the material the colleagues used right now, and we have two different materials which were nearly representative for the real cast dimension. And they showed a really good comparability between the single specimen and the multiple specimen method. And the deviation between these two methods was really small. It was lower than 6%. And we could show that also the number of necessary samples could be reduced for the single specimen method, and we only need 5 valid samples to evaluate the dynamic fracture toughness of ductile cast iron at -40 degrees. And the next step will be a further improvement of the crack propagation sensor to reduce the distance between the electroconductive lines to get more detailed view into this sample. Thank you for that.